series. Many people use the terms sequences and series interchangeably, but they are in fact different things. If we add all of the terms in an infinite sequence, we get an infinite series, or just a series. So we need to understand that a series is in fact a sum of the sequence. They are not interchangeable. Alright, so the notation we would say is that a sub 1 plus a sub 2 plus a sub 3 up through a sub n plus all the way through all the infinite terms. If we add all of that up, we get this sum of a sub n from 1 to infinity, and that is the series. Okay, so I hope you've seen this notation before, right? The sigma notation. Alright, so recall that this notation means sum. Right, means add things up. One of the things that we're particularly interested in when talking about series is if the series converges to a specific value. So to determine if a series converges, we have some notation we need to talk about. Given a series, let S sub n denote its nth partial sum. So S sub n represents the sum from 1 to n. So that would be a sub 1 plus a sub 2 through a sub n. This is not the infinite sum, right? It's not the infinite series, it's a partial series. If the sequence of partial sums, all right, so if the sequence S sub n, so that's S sub 1, S sub 2, S sub 3, S sub 4, through S sub n. So that's a series of partial sums. The first sum, the second sum, the third sum, up through the nth sum. If that sequence is convergent, and the limit as n approaches infinity of that sequence is some number s and exists as a real number, then we say that the series sigma a sub n is called convergent, and we write that sigma a sub n equals s. If that s exists, the number s is called the sum of the series. If, however, the sequence of partial sums is divergent, then we say that the series is divergent. Let's illustrate this with an example. Calculate the first 8 terms of the sequence of partial sums to 4 decimal places. Does it appear that the series is convergent or divergent? Okay, so calculate the first 8 terms of the sequence of partial sums. So that's the S sub n. So understand, what does this mean? We have this sigma n equals 1 to infinity of 1 over n cubed. That would be 1 over 1 cubed. That would be 1 plus 1/8 plus 1/27 plus 1/64 plus 1 1/25 plus 1 over 6 cubed is 216, I think. Let me just double check that. All right. Plus 1 over 7 cubed is 343. Plus 1 over 8 cubed is 512. Plus ... Alright, so that's what the series means, right? It's the sum of the terms of the sequence. Now, so now we want the sequence of partial sums. So now S sub 1 would be just 1. That's the first partial sum of this series. S sub 2 would be 1 plus 1/8. which is 1.125. S sub 3 would be 1 plus 1/8 plus 1/27, which is about 1.1620. You can verify this with a calculator. S sub 4 would be 1 plus 1/8 plus 1/27 plus 1/64, which is approximately 1.1777. S sub 5 would be all that plus 1/125th, which ends up being 1.1857. S sub 6 would be all that plus 1 over 216, which is approximately 1.1903. S sub 7, all the previous terms plus 1 over 343, which is approximately 1.1932. S sub 8 would be all the previous terms plus 1 over 512, which is approximately 1.1952. All right, so we look at that and we ask ourselves, does it appear that the series is convergent or divergent? Based on this, it appears to converge. It appears to be getting closer and closer, and I would just take a guess and say, and I'm not sure, is S, I'm putting a question mark above this, I'm going to guess S is equal to 1.2, and that's just a guess. I'm not sure about it. We're going to learn some techniques for some specific series where we can find the sum exactly, but right now I would just have to guess that it appears to be approaching 1.2. All right, so that's the idea. Now, through many of the sections of this unit, we're going to learn techniques to determine if a series converges using various analytical techniques. One common series that we'll deal with is called the geometric series. And the geometric series, basically, it's commonly noted as sigma a times r to the n minus 1. And so notice as n increases, each term has another factor of n. So the series is a plus a times r plus a times r squared plus a times r cubed, etc. This is called the geometric series. It can be shown that the geometric series is convergent if absolute r is less than 1, and its sum is given by a over 1 minus r. So that's the first term of the series. Over 1 minus r, and r is the common ratio. Not ration, ratio. If absolute r is greater than or equal to 1, then the geometric series is divergent. So let's remember what some of this notation means. It's convergent if absolute r is less than 1. That means that r is between -1 and 1. Whereas here, absolute r is greater than 1. That means if r is less than or equal to -1, or r is greater than or equal to +1. All right, so the series converges if r is between -1 and 1, non-inclusive. If r is outside -1 or 1, this geometric series diverges. Determine whether the series is convergent or divergent. If it is convergent, find the sum. And so here we have sigma n equals 1 to infinity of 1 over 3 to the n. We can easily write that as n equals 1 to infinity of 1/3 to the n. Now, this is not the formal form of the geometric series that was presented in the previous slide. because we don't have a times r to the n minus 1. Remember, we want this form, a times r to the n minus 1. So notice I could write this as sigma n equals 1 to infinity. I could, in a sense, take out a factor of 1/3. And so this would be 1/3 times 1/3 to the n minus 1. So the 1/3 is the a, and this 1/3 is the r. And so then, since r is between -1 and 1, we know it converges. And in fact, the series would be equal to 1/3 over 1 minus 1/3, where the numerator, that 1/3, is the a value, and the denominator, the 1/3, is the ratio. And so that would be 1/3 over 2/3, which is a half. And so the sum of the series is exactly 1/2. Let's consider another example. Here we're asked to determine whether the series is convergent or divergent. If it is convergent, find its sum. And here we have sigma n equals 0 to infinity. So let's be careful about that. N equals 0 to infinity of 4 to the n plus 1 over 5 to the n. Well, 4 to the n plus 1, well, isn't that 4 to the n times 4? So I can rewrite this as sigma n equals 0 to infinity of 4 times 4/5 to the n. Now again, this is at n equals 0, not n equals 1. So we have to be a little bit more careful with this. But now really what's happening here? N equals 0. We can adjust this by adjusting this n equals 0 and any appearance of n in the a sub n part. And so here's the idea. If we want to start at n equals 1, if we want this to be n equals 1, if we increase this, we have to decrease, right? So I increased by 1. I have to decrease by 1 any appearance of n in the a sub n part. So then this becomes sigma n equals 1 to infinity of 4 times 4/5 to the n minus 1. And so here what I see, this is now geometric with r equal to 4/5, so it is converging. And in fact, the series is equal to 4 over 1 minus 4/5, and so that would be 4 over 1/5, which would be 20. The series converges to exactly 20. Not all series that we're going to be looking at will be geometric series. We're going to be looking at a whole bunch of different kinds of series. And so we need to be able to determine some ways to figure out if the series will converge or diverge. One simple test for divergence is based on this theorem. The theorem says if the series is convergent, then the limit of the sequence is 0. If the series is convergent, then the limit of the sequence is 0. So, the contrapositive, if you know anything about logical statements, the contrapositive says, then, if the limit of the sequence does not exist, or if the limit is non-zero, then the series is divergent. So right away, we can determine if a series is divergent just by looking at the sequence of the terms. And if the sequence of the terms is, under limit, if the sequence of the terms does not limit to 0, then the series diverges. So let's consider this example. We want to determine if the series is convergent or divergent. If it is convergent, try to find its sum. And so we have the series n equals 1 to infinity of n squared over 3 times n plus 1 times n plus 2. All right, so what I'm going to do is I'm going to look at the limit as n approaches infinity of a sub n. And so that would be the limit with n approaching infinity of n squared over 3 by n plus 1 by n plus 2. And I'm going to switch over to a function notation so I can use the rules that we've learned for that. All right, so I'm going to now say, well, that's equivalent to the limit with x approaching infinity of x squared over 3 times x plus 1 by x plus 2. So that's the limit with x approaching infinity of x squared, and multiplying out the denominator, I'd have a 3x squared plus 9x plus 6. Now that's an infinity over infinity. I'm going to apply L'Hopital's rule. And so that would be the limit with x approaching infinity of 2x over 6x plus 9. That would again give me an infinity. I'll again, an infinity over infinity, an indeterminate form. I'll apply L'Hopital's rule again, and so this becomes then the limit as x approaches infinity of 2 over 6, which is exactly 1/3. So, that tells me then that the limit as n approaches infinity of a sub n is equal to 1/3, which is not 0. Since limit as n approaches infinity of a sub n is not equal to 0, sigma n equals 1 to infinity of a sub n diverges. And that's all. So we have that test for divergence. If the limit of a sub n is not equal to 0, then we know the series diverges. But can we state that, so can we say, well, what if the limit is 0? If the limit is 0, does the series necessarily converge? Well, the answer is no. I should say not necessarily. And so here is a common example that contradicts this statement. Let's consider sigma n equals 1 to infinity of 1 over n. This is often called the harmonic series. All right, so you should become familiar with that name, the harmonic series. And clearly, the limit as n approaches infinity of 1 over n is 0. But now let's consider this series. All right, so sigma n equals 1 to infinity of 1 over n. Well, that would be 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, a seventh, an eighth plus a ninth, a 10th, 11th, 12th, 13th, 14th, 15th, up through a 16th, a 17th, through the 32nd, the 33rd, 1/33rd, plus up through 1/64th, plus etc. And I've written it like this on purpose, and you'll understand why in a moment. All right, so now notice here, 1/3 is greater than 1/4. And so if I look at these two terms, 1/3 plus 1/4, those two terms are collectively greater than 1/2. Because 1/4 plus 1/4 is 1/2. So a number greater than 1/4 plus 1/4 must be greater than 1/2. All right, now let's look at the next terms. 1/5, 1/6, and 1/7. Each of those is greater than 1/8. 1/5 is greater than 1/8. 1/6 is greater than 1/8. 1/7 is greater than 1/8. So collectively, there are 1, 2, 3, 4 numbers that are greater than or equal to 1/8. And so collectively, these numbers are greater than 1/2. Let's look at the next grouping. 1/9, 10th, 11th, 12th, 13th, 14th, 15th. Each of those numbers is greater than 1/16. And there will be 8 of them, and so collectively those are greater than 1/2. 17th through 31st, each of those numbers, 1/17th, is greater than 1/32, and there will be 16 of them. And so collectively, those numbers are greater than 1/2. And we can continue this process. So that each grouping is greater than 1/2. And so what happens is, if we consider certain partial sums, we see that these partial sums keep on getting greater and greater. They do not approach any specific number. And so what we can say is this series diverges. Since each one of those partial sums ends up getting larger and larger, not approaching any specific value, this diverges. So, this is very important. Having the sequence converge to 0 does not imply that the series converges. It's very important to know. We have to develop other techniques to see if series converge besides the one we've already talked about, the geometric series. So let's consider an example. Determine whether the series is convergent or divergent. If it's convergent, find its sum. Here we have sigma 1 to infinity of 1 over n plus 2 to the n. Well, one of our facts about the summation notation is we can break this up. N equals 1 to infinity of 1 over n plus n equals 1 to infinity of 2 to the n. Well, this is the harmonic series, right? Harmonic series, which diverges. And this is geometric with r greater than 1. And this also diverges. and the series diverges. All right, let's look at another one. Determine if the series converges or diverges. If it's convergent, find its sum. All right, so sigma n equals 1 to infinity, 1 over 2 to the n minus 1 plus 2 over 3 to the n minus 1. All right, like I did before, let me break this up into 2. So n equals 1 to infinity of 1 over 2 to the n minus 1. Plus another sigma, n equals 1 to infinity of 2 over 3 to the n minus 1. All right, what am I going to do with that 2 to the n minus 1? Well, isn't 1 over 2 to the n minus 1, isn't that the same as 1 times 1/2 to the n minus 1? I mean, think about that. That would give me 1 to the n minus 1 over 2 to the n minus 1 times 1. That's fine. Plus sigma n equals 1 to infinity. And using the same idea, this would be 2 times 1/3 to the n minus 1. And each of these are geometric with r less than 1. So these are both geometric. With absolute r less than 1. So they converge. And we can be even more specific. We can find the sum. Let's see, the first sum would be 1 over 1 minus 1/2. The second sum would be 2 over 1 minus 1/3. 1 over 1 minus 1/2 is 1/2. 1 minus 1/2, or 1 divided by 1/2 is 2. Plus 2 over 1 minus 1/3, that would be 2 over 2/3, which would be 3. And so the sum of the series is 5. All right, let's consider one more example. Sigma n equals 1 to infinity of the natural log of n over n plus 1. And we want to know if the series converges or diverges. If it converges, we want to find its sum. All right, well, one approach to this is to rewrite this as sigma n equals 1 to infinity. The natural log of n over n plus 1, that would be the natural log of n minus the natural log of n plus 1. Now, to see if this converges or diverges, what I'm going to do is I'm going to consider a partial sum. I'm going to consider the nth partial sum of this sequence. So the nth partial sum would be a sub 1 plus a sub 2 plus a sub 3 plus a sub n minus 1 plus a sub n. All right, a sub 1 would be natural log of 1 minus natural log of 2 plus a sub 2 would be natural log of 2 plus natural log minus natural log of 3. Sorry about that. A sub 3 would be natural log of 3 minus natural log 4 plus a sub n minus 1 would be natural log of n minus 1 minus natural log of n. And then the nth term would be natural log of n minus natural log of n plus 1. So now look at what happens here. If we look at all the terms, I've got a minus natural log 2 and a plus natural log 2. I've got a minus natural log 3 and a plus natural log 3. I've got a minus natural log 4, and in the next term, there's going to be a plus natural log 4. Similarly, this natural log of n minus 1 is going to go away. And then in the second to last and last terms, I have a minus natural log n and a plus natural log n, and those will go away. So S sub n simplifies as natural log of 1 minus the natural log of n plus 1. Well, now the natural log of 1 is 0. So S sub n is simply negative natural log of n plus 1. All right, so now let's see. As n approaches infinity, S sub n would be negative natural log of infinity. Now, the natural log of infinity is infinity, so S sub n would approach negative infinity, which is not a real number. So the series diverges. If we had been able to find that S sub n approached a specific number as n approached infinity, we would have been able to say that the series converged. But we can't say that in this case. All right, that concludes this presentation.